What is question 3, Nikki?
It's sketch f of x equals the absolute value x plus 1 over regular x.
Cool.
And then it just says, that was part A, and then part B is evaluate the difference quotient and simplify the result for f of x equals square root of.
Okay, that's totally, yeah. Okay. So we're being asked to graph this function. And so what I would point out if I was graphing this function is, written it really terribly here. Where is it undefined? Right, so this is definitely undefined at x equal to -1. So we know we're going to have either some sort of vertical asymptote there or hole or something where it's not filled in. Everywhere else it is defined. So what I would probably try to do is actually plug in a few different values of x. There's an easy way to figure this out, and there's a more kind of longer way. So if I pick some numbers bigger than -1, like f of 1 is going to be 2 over 2, which is 1. F of 2 is going to be 3 over 3, which is 1. I want everybody in their head to pick a number bigger than -1. And now, if you plug in that number, what's the final result after you plug it in the top and the bottom and do the division? Did you get one? Did you get one? Did everybody get one? Right, everybody got one, because if x is bigger than -1, come on in. You're definitely going to get that f of x is equal to the absolute value of x plus 1 over x plus 1. But if x is bigger than -1, then x plus 1 is bigger than 0. And the absolute value of a positive number is just that positive number. But x plus 1 divided by x plus 1, as long as it's not 0 over 0, is just 1. And it's not 0 over 0 because we're saying x is bigger than -1. On the other side, if x is less than -1, now something different is going to happen, right? If I plug in like f of 0, sorry, that's not less than -1. F of -2, the absolute value of -2 plus 1 over -2 plus 1 is, the absolute value of -1 is 1 over -1, which is -1. If I try plugging in like f of -5, I'm going to get the absolute value of -5 plus 1 over -5 plus 1, which is the absolute value of -4 over -4, which is -1. Whatever we plug in that is less than -1 is going to give us a -1 for the same sort of reason. This f of x, if x is less than -1, f of x is still the absolute value of x plus 1 over x plus 1. Now here's how you show your work if you're actually trying to like be very, I don't know, rigorous. If x is negative, or if x plus 1 is negative, right, taking the absolute value of a negative number, how do you transform that negative number into a positive number? What do you multiply it by? -1. It feels kind of strange because you're saying I've got this negative thing and I'm going to take the negative of that to make it positive, but it's totally the right thing to do. And then the x plus 1 divided by x plus 1 still cancels and you get -1. Here's what this thing looks like. And I will say there is a similar problem on the practice test I posted, so you all should try that one as well. It's a little bit different, but pretty much the same. At -1, we know things are undefined. And then just when x is bigger than -1, the y values are positive ones. So I'm going to get an open circle right there, and then +1 all to the right. And then to the left, the y values are all going to equal -1. So still an open circle right there, and the horizontal line to the left as well. I don't think you need to show as much work as I've shown here, but I wanted to kind of give you the explanation behind what's going on as well as what you're actually. But typically, when you have an absolute value of something divided by the same something, it's usually 1 to one side and -1 to the other side. That is usually what you're going to get, because some of the time they're both the same sign, and some of the time they're both the opposite sign. So you get either a positive or a -1.
Could you go over like for some of the problems there's like the vertical, like it's a different type of equation, but you still have it, and Dr. Tab called it like the shadow zone. Can you go over determining like how it's positive and how it's negative on the graph, like which zone? Because you like plug numbers in on that number line, you have like the negative part, and then you have the middle part based on the zeros and the vertical asymptote.
Sure, but so I don't think this particular graph is a good example for that, but we can definitely look at a different one, which I think might be a better example.
Thank you.
Cool. Other questions about this? I'm gonna do that. I'm gonna look at the other question that you had first, and then we'll come back and we'll do another graph. All right. Moving on to, I believe it was 1 over x
It was.
or square root of x.
Square root of x plus 1.
Cool. So let's say our function is equal to the square root of x. I'm going to make it slightly different just for fun. Square root of x plus 2. We're being asked to find and simplify the difference quotient. Not take the limit, right? We're not being asked to use the limit definition of the derivative, although that's almost all the steps to get there. You just would not do one thing. So I want to find and simplify the difference quotient. Do you have to memorize the difference quotient? Probably. So what's the difference quotient? I would always start off by just writing out f of x plus h minus f of x over h. Always a good starting place if someone's asking for the difference quotient. And now we have to actually sub in. So you might off to the side over here say, okay, and also f of x plus h is the square root of x plus h plus 2. Or more generally, f of something is the square root of that something plus 2. And then I'm just filling in the x plus h. You don't have to write this up here, but it's nice to kind of be like, okay, I know a piece of thing. Yeah. So no. So there's 2 different questions, and we'll answer both of them. One question is find and simplify the difference quotient. And if it's that one, then we should not have a limit. The other question, which is very similar, is use the definition of the derivative or the limit definition of the derivative to find the derivative. And that's where you would do the limit of the difference quotient. So here we're just finding and simplifying the difference quotient. So if they don't say like use the definition of the derivative or the limit definition of the derivative, then we know we don't need a limit. So here we're going to get our f of x plus h, which is the square root of x plus h plus 2. I no longer need those parentheses because they aren't doing anything for me. They're not like, I don't have anything to distribute. Minus the square root of x plus 2 all divided by h. And when you see a square root minus the square root or a something plus or minus the square root in either the numerator or the denominator, that's a really good clue that we need to multiply by what? The conjugate. So we're going to multiply the top and bottom by the conjugate of the square root thing. That's going to be the square root of x plus h plus 2 plus the square root of x plus 2. When you're finding the conjugate, everything's the same except for the sign in the middle. And then the bottom has to be the same. Square root of x plus h plus 2 plus the square root of x plus 2. And then we multiply. So here's, and I would encourage you kind of want to not show all the work in this next step. Meaning the reason we're multiplying by the conjugate is because we know that when we multiply this by its conjugate, the middle terms cancel out. They add to 0. So you're just going to get the first thing squared. And you can even write it, I think it's not bad to write it as the square root of x plus h plus 2 squared. Middle terms cancel out, minus the second thing squared, which is the square root of x plus 2 squared. Divided by the things that aren't conjugates, you just want to leave as is. H times all of this. And I don't want to distribute the h in because what am I looking to eventually do here? Yeah, we want that original h. This guy right here, our ultimate goal is to cancel that guy. Sure, he can be a him. Cancel him. He's gone. We want him to go away. So let's see what we get here. Square root of x plus h plus 2 squared is x plus h plus 2. Square root of x plus 2 is x plus 2. I've made a mistake. We're going to fix it. So here's what I'm going to point out. If you make the mistake that I've made, things aren't going to cancel the right way, and the h's aren't going to cancel in the end. If we look here, if I look here, the x's will cancel, and 2 plus 2 is 4. And if I get h plus 4 divided by all the other stuff, I can't just cancel the h. It doesn't, I have to be able to factor it out. But I made a mistake, right? I forgot to put parentheses around here indicating that I should distribute that minus sign. So the point I really want to emphasize here is that if you're doing this simplifying the difference quotient thing, and you get to a place where you have not H things left in the numerator, it probably means you might have missed distributing a minus sign or something else like that, where the things didn't cancel like they were supposed to. Go back, look, be like, okay, what am I missing? So now x minus x is 0, 2 minus 2 is 0. So we're left with just h over h times all that stuff, square root of x plus h plus 2, plus the square root of x plus 2. And then finally, h divided by h is 1. So we're left with 1 over the square root of x plus h plus 2, plus the square root of x plus 2. And that would be our final answer in this instance. Just to answer Anthony's question there, if instead the question had been, use the definition to find the derivative of f of x equal to the square root of x plus 2, we would have taken all the same steps, except every step we would have needed to write what in front? The limit as, right. So we would have started off with the limit as h goes to 0 of, I'm going to skip this part and go to that part there. Square root of x plus h plus 2 minus the square root of x plus 2 all over h. We would have done the same things. We would have written equals limit of until we got to the very last step, which would have been equal to the limit as h goes to 0 of 1 over the square root of x plus h plus 2 plus the square root of x plus 2. And then once we have finally simplified the difference quotient as much as possible, then we plug in 0 for all the h's that remain. And doing that would get us 1 over the square root of x plus 0 plus 2 plus the square root of x plus 2. And then when you add something to itself, you've just got twice it. So that's going to be 1 over 2 times the square root of x plus 2. And that's how you do that question if there's a limit definition of the derivative of this question. I don't love how it is. Let me, sorry. I feel like in my own way here. There we go. Okay, that's a little better. Questions about that? All right. So there was a question about, and I'm not, oh, I'm dripping water everywhere. That's terrible. Sorry. It'll dry. Okay. So there was a question about this shadow thing, which I think I know what you're referring to, but I'm not 100% sure. So, and that's in the context of graphing. It looked like the graphing questions on the practice exam were not too terrible. Like they're not like ridiculous rational functions. It would look like it was like parabolas, straight lines, stuff like that. So let's say I want to graph. Sure, I want to graph both f of x equal to, I'm going to make something up. It's probably going to be terrible. We'll just start with this. X squared. Yeah, sure. Minus 5x minus 6. And we also want to graph g of x equal to, let's do that, James, sure. Negative x minus 2. Yeah, sure, that'll be fine. And so before we do anything, just so that we make sure we graph all the important stuff, we're first going to find where these intersect each other, because that's something you're being asked to do on your exam. So step 1, let's find the points of intersection. To do that, we just set each function equal to each other. So we're going to set x squared minus 5x minus 6 equal to negative x minus 2. And typically when I'm trying to solve an equation like this, I'm going to try and bring everything to the side where, I mean, it really doesn't matter which side, but I like the term that has x to the highest power to have a positive coefficient. So I would bring everything to the left here because I have a positive x squared on the left, and that's my highest power of x. So if I add x to both sides and add 2 to both sides, oops, and I've made an, yeah. What's that? It doesn't factor because I was just making it up as I went. So Do I want to fix it or just want to go with it not factoring? Yeah, I kind of want to fix it. So sure, 4. -4 is terrible. -5 would work. Let's change that -2 to a -1. Sorry about that. That's what happens when you're making things up on the fly. And I think that should work out now. We'll see. So I should point out though, sometimes things don't factor, which is unfortunate, but does happen sometimes. So just be aware, you might get something that doesn't factor, and you have to use the quadratic formula to find the solutions. But if we do it this way, we're going to get x squared, -5x plus x is -4x, and -6 plus 1 is -5. And I believe that should factor. This should factor is x minus 5 times x plus 1. So these x values here are going to be x equal to +5 and x equal to -1. And I should point out that that is not the answer to the question, what are the points of intersection? Because a point has an x and a y coordinate. So my points are going to be, well, if x is 5, the y value is going to be, well, g of 5 is -5 minus 1, which is -6. So 5, -6. I could have plugged it into that one, but it was easier to plug it into that one. And they should be the same because these are the values you got when we set them equal to each other. It is true. If you plug in x equal to 5 here, you get 25 minus 25 minus 6, which is -6. Similarly, if I plug in -1, well, -1 is 1 minus 1 is 0, which is not the y coordinate. It's the x. Sorry, it is the y coordinate. It's not the x coordinate. It's -1, 0. So those are my 2 points of intersection with these graphs. Now let's actually go about graphing them. And so this is where I might need some help with this shadow terminology because I'm not super familiar with it. Let's look at this f of x equal to x squared minus 5x minus 6. So what I think you're talking about with the shadow thing is try and find where this is positive or negative. Is that on the right track there? Oh, it's a sign chart. Okay, great. So if I'm really just going to find the intercepts first before I start finding the sign chart. And that's pretty typical when you've got either intercepts or vertical asymptotes. Those are the places where the sign might change. So if we set that equal to 0, this is factor as well. You get x minus 6 times x plus 1 equal to 0. So our important values that are going to go on our sign chart are going to be x equal to 6 and x equal to -1. Now, here's something that we see with experience. This is a parabola. It opens upwards, meaning on the ends, it's going to be up, and then it's going to be under, and then it's going to be up again. So I'm expecting my sign chart to be plus, minus, plus. I know it's going to be positive on the left and the right, and negative in the middle if it's going to be negative at all. Let's check and see. So on my sign chart, I get -1 and +6 and nothing else. And then picking a value larger than 6, so 7 minus 6 is positive, 7 plus 1 is positive, and their product is positive. Picking something between -1 and 6, like 0 minus 6 is negative, 0 plus 1 is positive, their product is negative. Or using the fact that each of these factors has an odd power, and the sign always changes when the power is odd, from there to there, since we're going over something that came from a factor with an odd power, the sign is going to change again. So our graph is above, then below, then above. That's just our graph of the parabola is above, below, above. We could also do a sign chart for the line. It feels maybe a little unnecessary, but we could do one if we wanted to, right? This line, g of x equal to -x minus 1. If you set that equal to 0, you do get -x equal to 1 or x equal to -1. So the sign chart, although a little boring, if you pick, sorry, you can't see that, a number larger than -1, like 5, -5 minus 1 is negative. Pick something like -3, -3 minus 1 is positive. So you can see the graph is going to go from being above to being below, which is not surprising, right? It's a straight line with a negative slope. So we're certainly expecting that to happen. Graphing this. I will say, if you have different colored pens and you're asked to graph two different functions, that might be a time to use pen on the test, just because it's easier for someone to distinguish the two different things you're graphing. I don't know. I would choose to do that if it were me, as I look for my other colored pens over here. Sure. So label our important points here. We've got this -1, and that's going to be where I have my intercept for my line. So my line is just going to look like this. What's that? Up because yeah, good call, because I totally put it in the wrong spot. That is, yeah. Woo, terrible. Sorry about, yeah. Awful. Just, yeah, good. Yeah. Yeah. I have nothing to say. Let's try that again. What's that? I could have, but then everything else would have been off kilter. So here's -1. And for our g of x equal to -x minus 1, the y-intercept is also going to be -1, because we set x equal to 0, we get y equal to -1. So then here's our straight line. Yeah, straight. We'll use the tools you've got. And then our parabola opens upwards, and ooh, yeah, it's going to be interesting. So it's x squared minus 5x minus 6. We know that the intercepts are going to be x equal to +6 and -1. So we have an intercept there, and also at +5. So we have an intercept there as well. So, and we also know that these graphs are supposed to intersect each other at the point when, oh, sorry, that's not, sorry, apologies, man, I'm just really saying a lot of wrong things there. Sorry, the graph's intercept was +6. Their graphs are intersecting at +5. So I should probably continue this graph down further. And say, okay, these are going to hit each other at 1, 2, 3, 4, 5, and then over here. So we're expecting this point of intersection. Sorry, this point of intersection. We've got this x-intercept, this x-intercept here at 6. And so we're looking at this kind of shape here. Let me ask you all, when you're graphing parabolas, are you expected to find the vertex? Okay. It's nice to know where the vertex is, but if we're not expected to, then we're just going to kind of eyeball it here. So look, oh, I should find the y-intercept though. That is something we are expected to find. Gosh, I'm just all over the place here. Our function here is x squared minus 5x minus 6. Clearly the y-intercept for that is going to be -6. So we're down about, yeah, about right there. So here's our graph. Kind of giant. So when graphing anything really, you're typically being expected to find any intercepts, y and x, as well as, at least if you're graphing two things on the same graph, you're typically being asked to find points of intersection as well. I don't feel like I did an excellent job on that example, so I apologize for that. It's not the worst thing ever. You did mention also asymptotes though, so I feel like we could look at a graph maybe where there are some asymptotes as well. But before I move along, are there questions about any of the things I've done here, other than correcting the mistakes? All right, let's look at a graph that has some asymptotes and see how to deal with that. Something that's not too terrible. Let's say something like, yeah, we'll do that. Screen here. Something like f of x equal to, yeah, let's do that. X minus 3 over x plus 1 squared. Or as it might be given to you, x minus 3 over x squared plus 2x plus 1. And there are good reasons to write it either way, really. So someone said to graph this, there are really, I think, 4 things we need to look for. Maybe 5 things. But the first things are the intercepts. So your y-intercept we're going to find by setting x equal to 0. So we're going to get f of 0 equal to 0 minus 3 over 0 plus 0 plus 1, which is just -3. X-intercepts, set the whole function equal to 0. We do that, x minus 3 over x squared plus 2x plus 1 equal to 0. When you're setting a rational function equal to 0, you really just need to set the top equal to 0. Question?
How would you know like whether to find the points of intersection or start off finding?
So this one, there aren't points of intersection. I'm only graphing one thing. I've just written it in 2 different ways. I've written it in the factored form and the multiplied out form. But I will say, if you were given 2 things to graph, I think it is good to, I mean, you really want to find all the things before you start graphing it. But definitely finding those points of intersection is good to do before you graph it, so you kind of have an idea of where the graphs are going to intersect each other. Solving this, we're going to get x equal to +3. So our y-intercept is 0, -3. Our x-intercept is 3, 0. And now for the asymptotes. For vertical asymptotes, we're going to find those by setting the denominator equal to 0. So we're going to set x plus 1 squared equal to 0, which is going to give us x plus 1 equal to 0, or x equal to -1. And that definitely is going to be a place where we are going to include on the sign chart when we're trying to figure out where this graph is positive, where this graph is negative. And then finally, horizontal asymptote. How do we find horizontal asymptotes again? You can look at the degrees, or you can look at the limit to infinity. The shortcut is degrees. I imagine on this first exam, they might want you to show more work. So I would say, either way, I would still write the limit to infinity. Because writing limit to infinity shows, okay, we know how we're supposed to do this. Limit as x goes to infinity of x minus 3 over x squared plus 2x plus 1. The shortcut answer here would be to say, well, since the degree on top is less than the degree on the bottom, the limit's going to be what? Right. But the longer way to do this is to divide everything by the highest power of x that's in the denominator. So if we wanted to show more work, we would divide everything by x squared. You'd get x over x squared minus 3 over x squared over x squared over x squared plus 2x over x squared plus 1 over x squared. Or you can factor out an x squared, that's also good. And then we simplify. X over x squared is 1 over x. And then x squared over x squared is 1. 2x over x squared is 2 over x. That's 1 over x squared. And then, and I know I've said this many times, as x gets really, really big, what happens to 1 over x? Yeah, it gets small. How about 3 over x squared? Also small. 2 over x, also small. 1 over x squared, also small. So we're left with 0 minus 0 divided by 1 plus 0 plus 0. And 0 divided by 1 is just 0. Or 0 divided by not 0 is just 0. And then we might as well give ourselves a little sign chart here. So for our sign chart, on the sign chart, you want to include all the x things, right? Because you're really looking at the x-axis when you're drawing the sign chart. So on the sign chart, I'm including my x-intercept of +3 and my vertical asymptote of -1. And I kind of, when I do the sign chart with the vertical asymptote, I kind of like to just like draw a little vertical asymptote in there. And for the 3, I know the graph is actually going to hit at 3. You can even like turn your sign chart into your graph. So then pick a number larger than 3, like 20. 20 minus 3 is positive. 20 plus 1 squared is also positive, and a positive divided by a positive is positive. And now either you can pick a number between -1 and 3. Well, we've already, you know what we should do? We should use our work efficiently. We've already picked a number between -1 and 3. We picked x equal to 0 over here and got y being a negative value. So I know if I pick a number between -1 and 3, the overall function should have a negative value. It's good to not do more work than we have to. And then finally, on the other side of -1, we could pick a number like -3. -3 minus 3 is negative. -3 plus 1 is negative, but a negative number squared is positive, and a negative over a positive is negative. Or we could have said -1 comes from this factor. This factor is raised to an even power, which means the sign is going to stay the same. And then we can kind of just draw our graph. We know we're going to be going down, down, down like that because it's a vertical asymptote, and then like that. And then we're going to hit that point there and then come up to the other side. So there's a good, it's not the full graph, but like there's a good idea of what our graph looks like. Let's get it a little, because let's draw it more nicely so that we have our y-axis as well. Oh my gosh, papers, come on. So drawing this a little bit more nicely, my y-intercept was -3. My x-intercept was +3. My vertical asymptote was -1. And then we know we're going to be going down this way. And then also down that way. So then we're going to come up, we're going to hit our y-intercept, we're going to keep going. We're going to hit our x-intercept, and we're going to cross from being negative to being positive. We'll leave that there for a second. So we've pretty much got all the stuff that happens in the middle. Now we just have to answer the question, what happens if you go way to the right or way to the left? Well, we found the horizontal asymptote, and the horizontal asymptote was y equals 0, which is kind of a pain. Right, when your horizontal asymptote is one of the axes, because you can't just draw it in, it's already there. So we're just saying, okay, eventually this graph has to turn around and get closer and closer and closer to the x-axis. Similarly, on the left, we're going to get closer and closer and closer to the x-axis as we go further and further to the left. And that's as good as we can do. I will mention here, eventually, when we learn how to find relative extrema, we will also be asked to find this point here where the graph has a relative maximum, and also this point over here where the graph has an inflection point. But that is future S problems, not current S problems. Hopefully that kind of addressed your question about graphing stuff, whoever was asking it. Okay. No, Maya, you're gonna know. Okay. Other questions from the practice exam or just in general?
I was able to do like the limits when that were on the budget then.
Uh-huh.
I was wondering just how you would do them with like fractions over fractions.
So like, can you give me an example? I think I know what you mean.
Let's say,
Can you read to me because I don't have the test on me?
it was 2 over x, and then putting that into the different expression.
Oh, cool. Yes, sure. So, and are we doing this as a limit definition of the derivative, or as a difference quotient? Either way.
Whichever, I just
Sure.
wanted to-
Okay, sure. So we're gonna say totally yes. I'm happy. In fact, I'm happy to make it a little bit more interesting. So let's say let's use the limit definition to find the derivative of f of x equal to, let's make it more interesting. Let's say 2 over x minus 5. I'll point out here, it says use the limit definition to find the derivative. Obviously, they mean the limit definition of the derivative to find the derivative, but we don't need to write that twice. So that's what they mean with the limit definition. So I'm always going to start off by writing the limit as h goes to 0 of just f of x plus h minus f of x all over h. Make sure that it's f of x plus h minus f of x all over h, right? It's a difference of two things. And then we're going to throw in all the stuff. So f of x plus h is going to be, instead of 2 over x minus 5, 2 over, in fact, I want you all to write out this next step on your own. Fill in those denominators. So for this first one, you should have 2 over x plus h minus 5. The second one, you should have 2 over x minus 5. The annoying thing about these specific ones where you have fractions right in front of the fraction is you do have to get the common denominator, and it's always going to be kind of gross. So the only thing to do here is to multiply the 2 over x minus 5 by x plus h minus 5 over x plus h minus 5. And to multiply the 2 over x plus h minus 5 by by x minus 5 over x minus 5. That's what we have to do. There is one way you can make writing this a little bit less terrible. So watch this for a second. We're going to write this as a limit as h goes to 0. I'm going to have 2 times x minus 5 minus 2 times x plus h minus 5 all over the common denominator x minus 5 times x plus h minus 5. And instead of writing all of that divided by h, we could instead say it's multiplied by what? Right. And that just kind of saves you from having to write fractions and fractions over and over again, which is just feels annoying. Any questions about from this step to this step? I probably could have taken an extra step and written it as 2 times x minus 5 over x minus 5 times x plus h minus 5 minus 2 times x plus h minus 5 over x minus 5 times x plus h minus 5. But we should see that we know we're getting a common denominator, so we can write this minus this over the entire same common denominator. That's why we're doing it this way. All right. Our expectation is that everything that doesn't have an h in the numerator is going to cancel out. So when we distribute these 2's here, we're going to get the limit as h goes to 0 of 2x minus 10 minus 2x minus 2h plus 10 all over. I would write this as one denominator now. I would write it as x minus 5 times x plus h minus 5 times h. It's totally fine to bring that h into the denominator over there. And let's see. 2x minus 2x is 0. Negative 10 plus 10 is 0. So I'm left with the limit as h approaches 0. You could probably skip this step, writing negative 2h over x minus 5 times x plus h minus 5 times h. You could probably just skip that and cancel the h's and say, oh yeah, h divided by h is 1. And now we're left with the limit as h goes to 0 of negative 2 over x minus 5 times x plus h minus 5. And now that I've simplified my difference quotient as much as possible, what do I do next? Right. Let me ask you, when I plug in 0, do I still write the limit? No. So I'm going to get negative 2 over x minus 5 times x plus 0 minus 5. But really, that's x minus 5 times x minus 5. And we should write that as negative 2 over x minus 5 squared. This one, we don't have the tools to verify it using the power rule, because you also need the chain rule to do this one. So you just have to kind of live with that. But there are other ones where you could just use, like the ones on the homework, on the exam, the practice exam, he said like do it and then also use the product rule, the power rule to verify that you did the right thing. Question?
Can you go finding the derivative function and then the tangent function?
Sure. So any specific type of function or just in general? Because so here's what I'll say. For the most part on this exam, I expect that any derivatives you're going to be finding are probably going to be using the limit definition. Whereas moving forward, you're going to be talking about power. So I should, so, but you have talked about the power rule in class, right? So I should briefly, yes, I'll get to that question, but let me take a detour here. You got time, yeah, we got time. So we should briefly talk about the power rule. Here's what the power rule says. I'm gonna tell you what it says, and then we'll kind of go back. If you take for f of x equal to x to any power, and that power can be a nice positive integer number, it could be a negative number, it can be a fraction, it can be an irrational number, it can be anything. The derivative is equal to that power times x to the one less power. That is the power. It's not hard to derive, but you probably did that in class. I will point out, if we wanted to show using the limit definition that the derivative, have you guys seen this notation, d dx? Okay, cool. That the derivative of x cubed is equal to 3x squared. The way we would do that is we would say, okay, well, the limit is, right, I see the words limit definition, I'm going to write down the limit definition. Limit as h goes to 0 of f of x plus h minus f of x all over h. My f of x here is x cubed. I'm going to get the limit as h goes to 0 of f of x plus h is going to be x plus h cubed minus x cubed all over h. I believe we talked about Pascal's triangle in this class. We did? Yeah, okay, I thought so. So, right, instead of like actually multiplying out x plus h cubed, you should do this. You should write a little Pascal's triangle over here. Like, oh yeah, x plus h cubed is going to be 1 times x cubed. And then the next coefficient is 3. The next power of x is 1 less times 1 more power of h. And that pattern just continues. This is giving you the coefficients, and the powers are just, the powers of x are getting 1 smaller, the powers of h are getting 1 bigger. That's going to be plus 3x to the first h squared plus 1 times h cubed. And then minus x cubed. I think I've written out too much. You should write this as x cubed plus 3x squared h plus 3x h squared plus h cubed, right? We don't need all those ones as coefficients and powers. And then just like every other time, the not h things cancel, and we're left with a bunch of things that have h in it. The limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed, all divided by h. You can either literally divide each thing by h, or if you prefer, you can factor out an h to cancel. Factoring out an h, I've got a 3x squared plus a 3xh plus an h squared all over h. Those h's cancel, and then plugging in 0 for the remaining h's, you get 3x squared plus 3x times 0 plus 0 squared, which is going to be 3x squared. And this kind of pattern happens regardless if it's x to the 3rd or x to the 30th. You get x to your highest power, which is going to cancel out with that thing there, and then you get that power times x to the 1 less power times 1h, and then a bunch of other terms that have more h's in them, so that when you factor out the 1h here, this first thing is the only thing left that doesn't end up having an h in it, and so that's all that's left in the derivative once you plug in the 0 for the h's, and that's why you're getting this power rule here. Power rule is nice. It's certainly nicer than doing all this every time you want to take the derivative of x to some power. So we should all together make sure we're comfortable with the power rule. Let's do a couple problems where we find some derivatives. For example, using the power rule, doing it the short way. So let's say, good job. I don't know why I'm not covering that up, but it's fine. So let's say f of x is equal to x to the 19th. G of x is equal to x to the, let's say the square root of x, and h of x is equal to 1 over x to the 7th. I want to find some derivatives. And a good rule of thumb is that before we find the derivative is almost always a good idea to simplify your expression as much as possible. I say almost, sometimes it's not, most of the time it is. For this first one, no big deal. It's already written as x to a power. The derivative is going to be 19 times x to the 18th power. Before I do this next one, I'm going to rewrite this as g of x equal to x to the 1/2 power. So that my derivative, g prime of x, is going to be 1/2 x to the negative 1/2. Same idea here. For h of x, before I take its derivative, I should rewrite it as x to the negative 7th power. So when I take its derivative, h prime of x is going to be -7 times x to the negative what? Right, because -7 minus a negative number subtracting one should always get more negative. Don't worry, I promise I'm coming back around to your question. We're taking a detour. So let's look at a couple more examples of this and then we will move back to it. Let's say our function was 3x to the 5th plus 7x squared minus 9x plus 2 over x to the 6th. And I want to find the derivative. I'm going to find the derivative. So what's the derivative of 3x to the 5th? Cool. You just use the constant multiple rule. So I want to point out, when we take the derivative of 3x to the 5th, what we're actually doing is we're saying, oh, the derivative is going to equal 3 times the derivative of x to the 5th, which is 5x to the 4th. Or as I like to say, this 3 that's a multiple of the function hangs out. Constant multiples hang out. We don't really think about it that way, right? We're just like, oh yeah, the 2 multiplies the 7 or the 5 multiplies the 3 or whatever. Like it works nicely every time. But really what we're doing here is we're using the constant multiple. We're saying, oh yeah, the 7 hangs out, the 2 comes down, 7 times 2 is 14. X to the 1st minus 9. You could use the power rule here if you wanted to. You could say you have a 9x to the 1st and the derivative is 9 times 1 times x to the 0th. But you shouldn't, right? You should just be like, hey, negative 9x is a straight line. And the derivative of a straight line with a slope of -9 is a slope of -9, right? Because the derivative is like the slope of the line or the slope of the tangent line. But for a straight line, any tangent line is the line. And then I should be thinking of this as 2 times x to the negative 6th. So its derivative is going to be minus 12 times x to the negative 7th. And we all just used the constant multiple rule and the sum difference rule. Because we had a bunch of functions added or subtracted together. And the way we took their derivative was by taking the derivative of each part and adding or subtracting the results together. So the constant multiple rule and the sum difference rule are rules that we kind of use all the time without ever really thinking about it. So in that same vein, I want you all to find the derivative of the following function. G of x is equal to, sure, 5x to the 7th minus 6x cubed plus, sure, 6 times the square root of x plus 4 over x to the 5th plus 9x plus 2. Sorry, that's a little long. Find that derivative. You might want to simplify a couple things first, specifically, or at least think about how to rewrite this and that. Another 15 seconds or so. All right, I think people are looking pretty done. So let's find our derivative here. So first of all, I'm not going to rewrite the whole thing, but I'm certainly going to think in my head, oh yeah, 6 times the square root of x is 6 times x to the 1/2. 4 over x to the 5th is 4 times x to the -5th. So now that I've written everything as something times x to a power, I can just use the power rule. So taking the derivative g prime of x, we're going to get 35x to the 6th minus 6 times 3 is 18x squared plus 6 times 1/2 is 3 times x to the -1/2. 4 times -5 is minus 20 x to the -6. The derivative of 9x is 9. The derivative of 2 is 0. Probably not right plus 0, but if you've already written the plus sign, you might as well toss the 0 in there. Cool. All right. Back to the question that originated all of this, which was use this kind of thing to find the equation of a tangent line. So let's say we want to find. Now the question is, do we want a function that's easy to differentiate, or do we want something that we're going to have to use a limit definition for? Good question. I feel like we've kind of done the two. So I will say, usually for a limit definition kind of question, you've only really got a couple varieties. You've got x to a power, which we now have a power rule for, but you should still, if you say, if the test says use the definition, even if you know the derivative of x to the 5th is 5x to the 4th, you still have to do it the long way. So make sure you read it carefully. The other thing I'll say is, and the other two types are something like 3 over x or 1 over x plus 4, like we did one like that. And the other type of thing is like a square root of x or a square root of 2x plus 1. Those are the three like varieties of limit definition derivative questions that typically get asked. Anything other than that is just too wacky to be on for a test anyway. So let's say we want to find the equation of the line tangent to f of x equal to, sure, let's say it's x to the 4th minus 3x squared at x equal to, sure, excuse me, positive 2. Why not? So when I see the words, find the equation of the line, what that makes me think is I need two things. Those things are a point and a slope. Those are the two pieces of information you have to find the equation line. Sometimes that appears as 2 points. Right, if you have 2 points, you definitely find the equation line through them because you have a point. You have 2 of them, and then you can find the slope between those 2 points. So, but we're always looking for a point and a slope. Do we have a point? I mean, you could kind of say this, but really I would say we have half a point. We have the x coordinate of a point. We also need the y coordinate. So our point here is going to be the point 2, f of 2. The x coordinate is 2, the y coordinate is whatever the y value is when you plug into. We plug into, let's see, f of 2 is 2 to the 4th minus 3 times 2 squared. That's going to be 2 to the 4th is 16 minus 3 times 4, and 16 minus 12 is 4. So our point is 2, 4. The slope is where we need to use the derivative. If they don't say to use the limit definition, then you can have free reign to use the power rule all you want. But if it's a function like the square root of x or 3 over x, actually both of those you can use the power rule for. If it's something more like square root of x minus 1 or 3 over x plus 2, we don't quite have the tools for that just yet. So it has to be really just something you can write as x to a power. So, but again, it's really just about reading the question. Does it say use the limit definition? Does it say use the power? Or does it not say that? Here, I'm going to find my slope by first finding the derivative. So the derivative is, well, the derivative of x to the fourth is 4x cubed. The derivative of minus 3x squared is minus 6x. That's our slope at any value of x. But our slope at x equal to 2 is going to be f prime of 2, which is going to be 4 times 2 cubed minus 6 times 2, which is going to be 4 times 8 minus 6 times 2, which is 32 minus 12, which is 20. And that is our slope. The rest of the question is remembering how to write the equation of the line. I personally prefer to use the point slope form. So if I was writing the equation, this green pen is not sure. Okay, I would write it as y minus the y coordinate equal to the slope times x minus the x coordinate. And then I would solve for y, because usually people want you to write the equation of the line as y equals mx plus b in the standard form. So then I would say y minus 4, distribute the 20 is 20x minus 40, and then I would add 4 to both sides to get y equal to 20x, and negative 40 plus 4 is negative 36. Or if you don't like that, you could also start off with y equals 20x plus b, and then plug in your x and your y coordinate. 4 equals 20 times 2 plus b. 20 times 2 is 40. 4 minus 40 is negative 36. But then you have to go back and plug in your b to get y equal to 20x minus 36. Either way is fine. Either way should get you to the same place. Personal preference. Nikki?
I thought that equation of the tangent line was a little bit more complex than the regular line.
Nope, definitely not.
Okay.
Tangent line is just the equation of the line. The only complicated part is typically finding the slope, really. Some of these people do write out no, it's really like you can write this out in different ways, but it's really not. It's really just find the point, find the slope, throw it into the usual equation of the line format, whichever you like. Other questions about that, or the other questions about that? Okay, Kelsey, and then Erica. Kelsey, you have a question? What's that?
Mine's not something else.
Okay, no, that's fine. Yeah. So moving. Oh, did you have a question about this, Erica?
No, thankfully, it's like not this.
Okay, let's go with Erica. So this is related. Then we'll go with Kelsey.
So like one of the homeworks, you have to like find like the different quotient kind of with the point. And with the plug in.
Sure. Yeah. Okay. Right. So let's actually look at this example in that way. So what if I had said use the limit definition, which is using the difference quotient. So we're going to use the limit definition to find, but instead of finding the general derivative f prime of x, we're going to find f prime of 2. Thanks. Always, yeah. Okay. So for some reason, writing it with the constant just seems very wrong to me, or feel like it's always like, how do I do this again? So what I'm going to do over here on the sides, I'm be like, well, I know that if I want to find f prime of x, it's the limit as h goes to 0 of f of x plus h minus f of x all over h. I'm like, okay, I know my definition of my derivative, but now I'm just going to replace the x with what? 2. So it's going to be the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. And I'll remind everybody that my function f of x is x to the 4th minus 3x squared, and f of 2 was equal to 16 minus 12, which is 4. Okay, it's still not going to be very nice, but that's okay. So f of 2 plus h, I might do over on the side and say, well, no, let's do it over here. Let's at least do the first step over here. So just throwing stuff into the function, f of 2 plus h is going to be 2 plus h to the 4th minus 3 times 2 plus h squared minus f of 2, which we just said was 4, all over h. Ooh, 2 plus h to the 4th. Here's where that Pascal's triangle is really going to come in handy. So I'm going to go down, I'm going to do Pascal's triangle until I get to the line that has a 4 in it. So here's what we're going to get when we do 2 plus h to the 4th. And you might just want to watch this for a second. So we're going to get 2 to the 4th plus 4 times 2 to the 1 less power times h to the 1 more power. Plus, what's my next coefficient? So 6 times 2 to the 1 less power, h to the 1 more power. Next coefficient. 4 times 2 to the 1 less power times h to the 1 more power. And finally, 1 times h to the 4th. I don't know if I'm gonna have enough room here. So minus 3. I'll also point out you can use Pascal's triangle for 2 plus h squared. It's just this row here. It's going to be 1 times 2 squared plus 2 times h plus h squared. Minus 4. Sorry, I'm sorry, it's terrible. Apologize for the squeezing it in over there. Put Pascal's triangle in the wrong spot. Hopefully you can see that a little bit better. Okay, let's simplify. So I'm gonna have I'm just gonna multiply things out. So 2 to the 4th is 16. 4 times 8 is 32h. 6 times 4 is 24h squared. 4 times 2 is 8h cubed. H to the 4th. And then I'm gonna distribute the minus 3. So you have minus 3 times 4, minus 3 times 4h, and minus 3 times h squared, and then a minus 4. And just like every other time we've done this, difference quotient, simplifying, we're really hoping that what kind of things cancel out in the numerator? Everything not h, the not h. Or you can also say, we hope that everything left in the numerator has an h in it. So let's see. So I've got so just identifying the not h's, my 16 and my negative 12 and my negative 4. Oh yeah, those add up to 0. I'm happy about that. 16 minus 12 minus 4 is 0. Cool. Let's combine the rest of the things, because you might also, sometimes some of the h things also do cancel out. That's okay. It's fine if they do. It doesn't always happen, but occasionally it does happen. So let's see. Let's look at the highest power of h first. I've got an 8h cubed. Sorry, I've got h to the 4th. That's my highest power of h. And you might just kind of circle things as you go. So h to the 4th I've dealt with, and then 8h cubed. There's no other h cubes, right? I thought there was before, but I was misseeing things. Dealt with that. And then I've got a 24h squared minus a 3h squared, which is going to be a 21h squared. And then finally, a 32h minus a 12h is a plus 20h, all divided by h. Since I'm almost out of room, instead of factoring out an h and then canceling out the 1h, let's just divide each thing by h, which means each power of h is just going to be 1 less than it was. So we're going to get the limit as h goes to 0. H to the 4th divided by h is h cubed. Some people do the same way. They like this and this and that and that to kind of see that you're dividing this thing by h. So, and then 8h cubed divided by h is 8h squared. 21h squared divided by h is 21h. And 20h divided by h is 20. And then as h goes to 0, what are we going to get? 0 minus 0 plus 0 plus 20, which is 20. Which was the same slope we got doing it the other way. So hopefully this is a good example of what you're looking for, Erica. So definitely when you're finding the difference quotient at a particular point, it's the same as the general thing, except you're just replacing x with an actual number. Cool. That's good. I like that question. Good question. Kelsey. Yeah, definitely. It's definitely on my. It was on my agenda for today. It's just we got going in different directions. So let's look at some continuity examples. Sure, let's do that one. Let's say we have the following function. G of x equal to, that's a good one. Square root of x plus 7 minus 3 over x minus 2 when x is not equal to 2. And 1/6 when x is equal to 2. So I feel like the way your teacher is more likely to phrase a question like this is, actually, I don't know about this. He can go either way. He could just say, show this function is continuous at 2, or show it's not continuous at 2. Or he could say, determine whether or not it's continuous at 2. Or he could say, where is this function continuous? Certainly 2 is in question. I would also point out that the top function isn't continuous everywhere. Or I should say the first piece here, that top function may or may not be continuous at 2, taking this into account, but certainly x plus 7 has to be greater than or equal to 0. So we know that we're limited to x being greater than or equal to -7. So we're talking about where the entire thing is continuous. Here's -7, here's +2. We're going to get everything between -7 and 2 and 2 to infinity. And then we're just going to look at what's happening at 2. So our answer here is either going to be -7 to infinity or -7 to 2 union 2 to infinity. And it's all going to depend on whether or not we get to include 2 or not. So I don't know if you'd ask it this way, but I would just point out that usually when the question gets asked this way, like where is the function continuous, the place where things are getting broken up is obviously a place we have to look at, but sometimes there are other restrictions as well that are going to limit the interval of continuity. All right, so if you're looking to show a function is either continuous or discontinuous, you should always start off with the same 3 things. The first thing, so again, for continuity at 2, so at x equal to 2, the first thing we're going to look at is, does g of 2 exist? What you should do, if you shouldn't write, I wouldn't suggest you write does g of 2 exist. You should ask that question in your head, and then you should write the answer is g of 2 doesn't exist, or g of 2 is equal to whatever it's equal to, which in this case it's just given as 1/6. There is no work to show. If x is 2, g of 2 is 1/6. Okay, the second piece is, or the second question you should ask yourself is, does the limit as x approaches 2 of g of x exist? I should ask you all, if the answer had been that g of 2 didn't exist, what do we get to say then? Is the function continuous at 2? No. So if any of your answers to any of these 3 questions are no, then you automatically get to say, great, the function is not continuous at that point. If all the answers are yes, then it's continuous at that point. So does the limit exist? So let's see. If I take the limit as x approaches 2, I will point out here, I don't have to use one-sided limits because the function is the same on the right side of 2 as it is on the left side of 2. If x is bigger than 2, g of x is equal to this. If x is less than 2, g of x is also equal to this, because it's always equal to this as long as x is not 2, either on the right or on the left. So when I do the limit as x approaches 2, it's just going to be the limit as x approaches 2 of the square root of x plus 7 minus 3 over x minus 2, which is definitely a 0 over 0 type of limit. Right? If you plug in 2, you're going to get 0 over 0, which means you have to do some work. And just like a different problem we did, we're going to have to multiply by the conjugate. Square. I should be clear here. The conjugate of the part that has the square root. So the square root could be in the denominator, it could be in the numerator. It's always whichever part has the square root, because you're trying to multiply it out so you no longer have a radical. So square root of x plus 7 plus 3 over the square root of x plus 7 plus 3. So that's going to equal the limit as x approaches 2 of x plus 7 minus 3 squared is minus 9 over, I don't want to multiply out the bottom. The things that aren't conjugates, you just want to leave as parentheses x minus 2 times parentheses square root of x plus 7 plus 3. Since I'm tight on space here, I would point out that x plus 7 minus 9 is x minus 2. And x minus 2 divided by x minus 2 is going to give me a 1 in the numerator. So I have the limit as x approaches 2 of 1 over the square root of x plus 7 plus 3. Plugging in 2, I get 1 over 3 plus 3, which is 1/6. So the limit does exist. Great. Limit as x approaches 2 of g of x is equal to 1/6. And then finally, the question, and really this is where I would say you get to answer the question if you haven't already determined that it's discontinuous. You can say, if those values are the same, then yeah, it's continuous. Or if those values are not the same, then no, it's not continuous. So g of x is continuous at x equal to 2 because the limit as x approaches 2 of g of x is equal to g of 2. So to go back and if the question was just, is this continuous at 2? The answer is yes. If the question was, where is this continuous? Then the answer is everywhere from -7 to infinity. Because it includes everything from -7 to infinity, including 2. Oh, it's 10:15. All right. We can do one more, or someone else has a different type of question that is also fine. I feel like we should do one more, but if there's something else that's really burning in your brain, we can address that. Yeah, Anthony.
Okay, so I was saying 1.6, and there was a question where it's like a rational function.
Yeah.
It's continuous.
Uh-huh.
And there was another one that wasn't continuous.
Okay. So
Do you want me to like show you?
I think I can come up with a couple examples. So let's say we have these two functions. F of x equal to 2x squared plus plus is fine. Plus sure 4x plus 6 over x squared plus 9 versus g of x equal to x minus 1 cubed over x squared minus minus 4x minus 8. Yeah, that's good. Nope, not 8. Sorry. 12. Sorry. All right. So first and foremost, I would say both of these functions are continuous almost everywhere, at least. Where is f of x continuous? Okay, when you get asked this question, the real question is, where is it not continuous? Rational functions, polynomials divided by polynomials, are continuous on their domains. So when you're asking where is this continuous, or when you're really asking where is it not, you're really just asking where is it undefined? And then I should say this is for rational functions specifically. There are other functions this is also true for, but we're not getting into those right now. So let's see. Well, for f of x, a rational function is only undefined if its denominator is equal to 0. So we're going to set the denominator equal to 0 and try to solve. But if we try to solve this, we get x squared equal to -9, and there's no real numbers. There are solutions there. So here we're getting no solutions, which means it's not undefined anywhere, which means it's continuous. I should say f of x is continuous everywhere. On the other hand, g of x is certainly undefined when the denominator x squared minus 4x minus 12 is equal to 0. And I believe that factors as x minus 6 times x plus 2. So it's undefined when x is equal to 6 and x is equal to -2. So I would say g of x is continuous everywhere but -2 and 6. So we're getting all of this and all of this and all of this. So g of x, broadly, you could say g of x is discontinuous. But to answer the question more accurately, we should say g of x is continuous on the interval -infinity to -2 exclusive union -2 to 6 exclusive union 6 to infinity. Do grab a practice exam if you're leaving, or even if you're not. So that's how we'd answer that question. This function is continuous everywhere because it doesn't have any places it's undefined. This function is continuous on this interval because it's undefined, -2 and +6. All right, should call it there. So I'll say there's a practice exam over there. You should all grab one. If you're virtual, it is posted on Canvas, and I will post the solutions to it later today. But I want to give you all a chance to look at it without having access to the solution, so you can try to practice it. Take it. It's very similar to the exam he posted. Try to take it like an actual exam. Give yourself like 50 minutes with just a pencil and whatever else you're allowed to have, and then after you've given yourself 50 minutes, then look at the solutions. And best of luck tomorrow. I think you all do great.